In statistics, correlation is used to describe the linear relationship between two quantitative variables. By relationship, we mean that the values of one variable changes as the values of the other variable changes. By linear, we mean that the relationship can be described by a straight line. Suppose we call the two quantitative variables x and y with this hypothetical data. We can visualize the points in a graph called scatter diagram or scatter plot. You can see here that as x increases, y also tends to increase. When x is low, y is low. And when x is high, y is also high. We refer to this as a positive correlation, as the scatter plot goes from lower left to top right. On the other hand, if y decreases as x increases, we have a negative correlation, and the scatter plot goes from top left to lower right. Here we have a set of scatter diagrams with positive correlation. The first one here depicts a perfect positive correlation, where all the points will lie on a straight line drawn through them. The second one shows a very strong positive correlation. The points are very close to forming a straight line. The linear relationship in the third one is also positive and strong, while in the last one the relationship is still positive but weak. And here are a set of negative relationships: perfect, very strong, strong, and weak. Now we have a measure of the linear correlation called the correlation coefficient, or Pearson's R. It is represented by the letter R. It can take on values only between -1 and 1, and it describes both the strength and the direction of the relationship. The absolute value of R tells us about how strong the relationship is. The stronger the correlation, the larger the absolute value of the correlation coefficient. The sign on the coefficient, positive or negative, tells us about the direction of the relationship. So when R is -1, we have a perfect negative correlation, and when R is +1, the relationship is positive and perfect. The closer R is to -1 or 1, the stronger the correlation. The closer R is to 0, the weaker the correlation. And when R equals 0, we say there is no correlation. So R equals -0.87 will be considered strong, R equals 0.42 will be moderate, and R equals 0.13 will be considered weak. There is no general agreement on what values of R represent weak, moderate, and strong correlation because of several other factors like sample size. In some cases, R equals 0.5 is considered moderate, while in some cases it is considered strong. So I will leave it to you to check your textbook or course for their guideline on how to categorize correlation strength. Now let's look at a quick question. Which of these correlation coefficients indicates the strongest correlation? The highest value here is +1.23, which unfortunately cannot be a correlation coefficient because it is greater than 1. So the answer is -0.87 because it has the largest absolute value between -1 and 1, and the weakest will be +0.08. The correlation coefficient can be calculated in different ways, depending on what is available, either by using formula or software. Note that swapping the positions of x and y here does not change the value of the correlation coefficient. That is, the correlation between x and y is the same between y and x. Here are some scatter diagrams with their corresponding correlation coefficients. Positive correlations at the top and negative correlations at the bottom. And here we have practically no correlation, as it is difficult to approximate these points by a single straight line. These curves and circle, however, show some clear relationships, but none of them can be well represented by a straight line. So as far as correlation is concerned here, the correlation coefficients for these are approximately 0. Now consider this case where the points cluster together enough to be represented by a straight line. would you expect the correlation coefficient to be close to 0 or to 1? You might say 1 because the graph satisfies the straight line requirement. But that would be incorrect because the values of y are neither increasing nor decreasing as x increases. That is, the values of y are pretty much constant. So the correlation will be close to 0. Likewise here, the correlation is close to 0 because y increases and decreases without x changing in value. Now, if two variables have a strong correlation, we do not say that one affects or causes the other to change without further analysis. For example, if there is a strong positive correlation between class attendance and grades, we do not conclude that class attendance causes grades to increase. It is possible that the same students who regularly attend class also consistently do their homework, watch related videos, and do a lot of practice. So correlation does not imply causation or causality. We can say that as class attendance increases, grades also increase. But we do not say that increase in class attendance causes grades to increase. That is, without performing an experiment. So to wrap it up, we looked at how scatter plots are used to display relationship between two quantitative variables. We showed that correlation coefficient R is a number between -1 and 1 and is used to describe the strength and direction of a linear relationship. We stated that correlation coefficient can be obtained using formula or software, and that correlation does not imply causation. And that's it. Thanks for watching.